For this next example, we're going to use this graph here of the function 1 over the cube root of 27 minus x to kind of get an idea of what we think the answer might be before we actually get to the calculations. So I graphed 1 over the cube root of 27 minus x on the window from -1 to 27, and the y window was 0 to 3, and this is what came up. And as I pay attention to what's going on here, 0 is not an issue for x, because certainly I can find the cube root of 27 easily to be 3. But if I plug in 27 for x, I'm going to be dividing by 0. So that tells me I have a vertical asymptote at x equals 27, as indicated by the graph. So what we want to do, according to this integral, is we want to accumulate the region from 0 to 27. So we're talking about this space right in here. And notice that the y value here, the y window, only goes up to 3. And actually the graph was a lot closer to the asymptote, the vertical asymptote, than what I can show here. Okay, but this graph actually gets so close here that it almost pinches off this little region right here. So if I had to guess, does this integral converge or diverge? Does it go to infinity or does it level off at some area? I'm thinking, just based on the graph and this small window setting for y, that this graph is going to converge. I think I'm going to get a value for the answer, not an infinity. But that'll, we'll see what's going to happen when we work it out. Okay, it's an improper integral because this upper limit 27 causes us to divide by 0. So let's rewrite it as a proper integral. So the upper limit b is the problem. I'm going to approach 27. And as I approach 27, I'm approaching the asymptote, so I'm approaching 27 from the left. I'm going to bring up the cube root as a -1/3 power. Finding an antiderivative is going to require u substitution, where u is the inside function 27 minus x and du is negative dx. So it looks like I'm going to have to bring in a negative and pull out a negative, which I'll put in front of the limit. See if I can write down a little bit here and use this space. Looks like it's going to be u to the -1/3 du. And that's just going to be a reverse power rule. So u is going to increase to 2/3, and I'm going to multiply by 3/2. And I'm going to evaluate that from 0 to b. To make the evaluation part a little bit easier, I think what I'll do is I will pull the 3/2 in front. I already have the negative there, so that becomes -3/2. Okay, so the 3/2 is out of the way. All I have to do is switch back to x, 27 minus x raised to the 2/3. Which we'll be evaluating from 0 to b. Okay, now ready for the evaluation part of it, replacing b in for x and 0 in for x. So 27 minus b to the 2/3 minus 27 minus 0 to the 2/3. Let me squeeze that in here. Let's see, I think I need to do a little cleanup over here first before I put in 27 from the left here. So this just becomes 27 to the 2/3 power. Let's look at that for just a second. I'm going to come down here and just kind of think about how I can make this a little easier if I didn't have a calculator. This is one of those ones where I mentioned that you might want to rewrite this as a power. 27 is 3 cubed. Okay, and then I'm going to raise that to the 2/3 power. So multiplying the exponents, 3 times 2/3, 3 over 1 times 2/3. The 3's will cancel, so it's really just 3 squared. That's not too bad. That's 9. I'm ready to evaluate the limit, so I'm going to lose that limit statement because I'm going to plug in 27 from the left. If I think about numbers that are smaller to the left of 27, like 26.9, 26.99, 26.999, etc., and on, 27 minus that number is going to be close to 0. So what I'm thinking here is 27 minus 27. I'm going to go ahead and put 27 in. That'll work. That's just going to be 0, and I still have the minus 9. I'm going to come down here. So I've got negative 3/2 times, well, that just goes to 0. 0 to the 2/3 is something I can calculate. So that's just 0. 0 minus 9 is negative 9. And multiplying is going to give me positive 27/2, 13.5. That makes sense. It's a positive number. I think it should be because of the placement of the graph above the x-axis. And it doesn't diverge. It converges to 13.5. This last example has us look at an improper integral where there's an asymptote in between the limits. So if you were to graph 1 over x minus 1 to the 2/3, you're going to have a vertical asymptote at 1. So we're going to actually have to use properties of integrals and rewrite this as a sum of 2 other integrals. Okay, so we need to be aware of where does that vertical asymptote occur, because in this situation, that's where we want to break the integral. So it's at 1, so it's going to be 0 to 1 plus 1 to 3. And oh thrill here, we've got 2 problems in 1. Alright, okay, taking care of a few things here. I know that I need to replace 1 with b in this integral, and I'll replace 1 with a in this integral, and I'll also pull up the denominator. Okay, and think about what we're doing here. We're approaching 1 from the left side. So if our x values go from 0 to 1 and I'm in that interval there, I'm approaching 1 from the left. And we'll replace this with b. Bringing up the denominator, x minus 1 to the negative 2/3 dx. Let's rewrite the other improper integral in a proper format. So the limit as, and here we have a, the vertical asymptote down here. We're going to approach a from the, now think about, we're in between 1 and 3, and we're going to go back to 1. So we're approaching 1 from the right side of the integral from 1 to 3. So approaching 1 from the right-hand side, we're coming back to 1 from the 3. The lower limit here is going to be our a value, and then we go to 3. I guess one good thing about this when you have to split it apart is that once you find one antiderivative, you've got both of them. Okay, so now we're ready to integrate. It looks like it's going to be u substitution. It's not too bad though. U is the inside function and du is dx. So I don't have to bring anything in. So let me see if I can kind of get to the antiderivative pretty quickly. So the limit as b approaches 1 from the left. I'm going to integrate, so I lose the integral symbol. Okay, this is going to be u to the negative 2/3 du. So that's going to be u raised to the 1/3 power divided by 1/3, which is the same thing as multiplying by 3. So 3 times, I'm going to try and avoid the u substitution here and just kind of do it mentally. Increase to 1/3, divide by 1/3, or multiply by 3. This is going to be 1/3, or the cube root of x minus 1. Okay, and we're going to evaluate that from 0 to b. Okay, integrating as well here, it's the same antiderivative. So 3 times quantity x minus 1 to the 1/3, but with new limits, a to 3. Okay, so now it's just a bunch of calculations. Okay. I do see that right here and over here that I'm going to be able to pull the 3 out. That might make our work a little bit easier, so I'm going to do 3 out front. Okay, so by my moving the 3 out front, I'm just plugging in b for x. So b minus 1 to the 1/3, or cube root, minus, plug in 0, 0 minus 1 to the 1/3 power. Okay, this is a plus. For this one as well, I'm going to pull the 3 out front. I can tell it's going to get crowded. The limit as a goes to 1 from the right. Okay, and so here, plugging in 3 minus 1 to the 1/3. So 2 to the 1/3 minus, and now I have to plug in a, so a minus 1 to the 1/3. So minus a minus 1 to the 1/3. It's getting kind of crowded there. Okay, coming down here. 3 times, so I'm ready to deal with this part of the problem. I'm ready to plug in 1 from the left. Go ahead and just plug in 1 and see if it works, and if not, we'd have to adjust, try and figure out something else to do. But I can plug 1 in here and that just gives me 0. That's really nice. So plugging 1 in here, I get 0 raised to the 1/3, just 0, minus negative 1 to the 1/3, which is just cube root, plus 3 times, okay, and then right here I have 2 to the 1/3, or the cube root of 2, minus, plug in 1 for a, so that's 1 minus 1 to the 1/3. So things are going to be able to clean up for us. Alright, so 3 times, that's 0, cube root of negative 1 is negative 1, opposite of negative 1 is 1. So all of this goes to 1, plus 3 times, and then let's work on this right here. So that's just the cube root of 2, and this is just 0 to the 1/3, which is just 0. So it looks like my answer is just 3 plus 3 times the cube root of 2, whether you want to factor out the 3 or not. So it looks like that one also converges. You could check it with the calculator by putting the function in and then using the appropriate keystrokes. In this example, let's use the graph to help us understand what we're finding. It says let f of x equal twice the natural log of x. Here we go. And let R be the unbounded region in the 4th quadrant above the graph of f. So we're in the 4th quadrant above the graph of f. They must be talking about us accumulating this region right here. Okay, we do have a vertical asymptote at x equals 0, the y-axis, but it looks like as the graph comes down here that it's getting really close to the y-axis pretty quickly. So it looks like it's almost pinching off a specific area. If I had to guess, I would just say that this is probably going to be a convergent integral. It is going to approach some number. And if we think about it, the value of the integral that represents this region, the value of the integral should be negative. Okay, so let's see if we can set up the integral that represents that area. So we've got an integral from 0 to 1 of 2 ln x dx. Okay, and if we just look at this right here, is it the first thing you want to think about is anytime you encounter an integral from now on, is it an improper integral? And those that have infinity limits, you know, that's very obvious, but it does with ones that don't have infinity as limits, it does require us to kind of pause and look at what's happening. And you might want to think about the natural log graph and how there is a vertical asymptote at x equals 0. So this would be an improper integral. I think I'm going to pull the 2 out as well when I rewrite it. So 2 times the limit as, and 0 is the issue here, and that's in the lower limit position. So as a approaches 0 from the right, I'm going back to 0 of the integral of natural log of x dx. So time for integration here, finding an antiderivative. And without going through all the time and effort here, natural log of x would be a good antiderivative to try and memorize. We found that antiderivative by integration by parts. So I'm going to find that antiderivative. 2 times the limit as a approaches 0 from the right. And the antiderivative is x ln x minus x. With limits, here's a and here's 1. Limits of a and 1. I think there's been too many videos done today. Equals twice. Let me do the evaluation part of the FTC. I'll leave some pretty big spaces here because I have 2 terms to evaluate. So let's plug in 1. So 1 times the natural log of 1, which I'm going to come back later and make that 0, minus 1. Plug in a ln a minus a. Okay, a little cleanup here, and then we'll evaluate the limit. So natural log of 1 is 0. So that becomes negative 1 minus a ln a minus a. So a little cleanup. Now let's evaluate the limit. Twice, you lose the limit. So I have negative 1 minus, just go ahead and plug in 0 if you can. If it works, great. 0 times ln of 0, which that doesn't make any sense, but that's okay because I'm multiplying it by 0, saved by 0, minus 0 here. So again, this product is 0. Minus 0 is just 0 for the whole thing. So I end up with 2 times negative 1. So we did end up with a negative value as we thought because of the graph here. Alright, so as a final example, I know you guys have a graph on your paper. Like I said, I just didn't copy over through the, the software program that I was using to try and take a worksheet and change it to a Word document. Okay, but we know what the reciprocal graph looks like. It looks like this. Okay, and then we're asked to find the unbounded region in the first and fourth quadrants that lie between the graph of f and the x-axis from negative 2 to 2. So just real quickly looking at what we are being asked to find is this region, first and fourth quadrant. Oh, that doesn't make sense. Hang on. Yeah, interesting. I haven't noticed that before. I'm not sure where I got the worksheet from. I think at a workshop or something, but I think this is a typo. It's on your worksheet. It's on my worksheet. It's the way it came to me, but it doesn't make sense for our graph. The unbounded region in the first and fourth quadrant. That should be third. That should be the third quadrant there. Interesting. That lies between the graph of f and the x-axis over the interval from negative 2 to positive 2. Yeah, that wouldn't make sense in the fourth quadrant. Interesting. Okay. So now that we've fixed that for the first and third quadrant, we're talking about this space right in here. Okay. So that's what we want to look at finding. So when you think about the setup of the integral from negative 2 to 2 of the reciprocal function, okay, we don't have an infinity limit, but we do see that we're crossing over the vertical asymptote at x equals 0, so we would have to split this into 2 integrals from negative 2 to 0, and then from 0 to 2, rewriting each as a proper integral. Well, at this point we don't have time to solve it, but that's how you would proceed with this problem. So I encourage you to just go through the practice and see if you can do that one, and we can check back later with each other and see what you guys ended up with.